Hello, and welcome to Astronomy 100. In a previous segment, we talked about Stefan's law, and we talked about how the energy that is emitted by an object is related to the temperature of the object that's emitting the light. So what we're going to do in this segment is we're going to show how we can take that concept and turn it into a relationship that allows us to measure the temperature of an object just by looking at the light that comes from the object. Now here are the key concepts. From the concept of Stefan's law, we understand that if every object in the universe has a temperature associated with it, and we saw in a previous segment how everything in the universe has to have a temperature, then therefore everything in the universe has to emit energy related to the temperature of that object. And that's what Stefan's law is. Everything with a T has to have an E, or an energy associated with it. To be able to turn this into something workable so that we can determine the temperature of a body that's emitting light, we have to invoke an idea from physics called blackbody. Now, blackbody is a little bit confusing to people because the term itself implies an actual object. For instance, there is no such thing as a black body. The example I'll give you is this piece of coal is a black object, or you might want to say it's a black body. But the term black body radiation is not referring to an object, it's referring to a behavior that an object has. So we won't say that this object is a black body, but we can say that there are objects in our universe that have black body behavior. So black body radiation is the light that comes off of an object that is behaving with black body behavior. There are three rules that go with black body behavior, and these rules are the result of what we call in physics thermodynamics. Thermodynamics is the energy that's associated with the temperature of an object, so thermodynamic. And the three rules, I'm going to show them to you as three separate rules, but black body behavior is all three of these rules happening simultaneously. The first one is, for an object to behave with black body behavior, it has to be an object that reflects no light that shines on it. The second rule is that for it to have black body behavior, it must be an object that absorbs all light that falls upon it. And for an object to have black body behavior, it must also emit light only as a result of its temperature. So all three of these have to be in place at the same time. To understand how reflection and absorption and emission are related to each other, we pre-recorded a demonstration that will show you the differences and the similarities between these three principles. Okay, in this demonstration, what we're going to do is demonstrate the properties of reflection and absorption and emission. And to do this demonstration, I have a very simple setup in front of me here. I have a row of lights. Three lights in particular are of different colors. I have a blue light, a green light, and a red light. And then I have a source of white light. And if you recall from a previous section, to be in the category of truly white light, light has to have all of the colors of the rainbow present, and then of course in combination. So white light is all colors of the rainbow present. They don't have to be in equal quantity, but they have to all be there. And so to begin the demonstration, what I'd like to start with is something that is very black in appearance. And this is just a piece of coal, and it is one of the blackest things that I can think of that I have in my collection that is natural. So this is one of the blackest things you can find in nature. Now, the definition of black is the absence of all color, whereas the definition of white is the presence of all color. So these are sort of opposites to each other. And the first piece of paper I want to show you is just a standard piece of Xerox paper that you would have from a Xerox machine. And it is appearing white to your eyes because it has the ability to reflect all of the colors that it's being given to you. So this source of white light has to have all colors of the rainbow present to be able to have the piece of paper reflect all of those colors to you. The paper has to have something about its property to allow that to happen. And in this case, to get a white sheet of paper, they actually bleach the paper. And the wood pulp normally has a natural color to it, so they bleach all the color out of it to give us the appearance of a white sheet of paper. This sheet of paper that, let's for all intents and purposes call it red, even though it looks a little pink. This sheet of paper looks red because the pigment that's in this paper has the ability to bounce or reflect red to your eyes. And so it demonstrates that there must be red present in this source. Otherwise, if we don't give the sheet of paper red, it can't reflect that red to your eyes. Similarly, there must be yellow in this light source to be able to have you see yellow reflected from the yellow sheet of paper. The green sheet of paper looks green because there's green in the source. Then the green light hits the paper, reflects off the paper, and goes to your eyes. And then lastly, I have a blue sheet of paper. There must be blue in this light source because the blue light reflects off of the paper. The paper has a pigment to it that allows the blue to reflect to your eyes. Now, what I want to do to show you how this can really be seen in a very, very different way is if I get rid of the white light, and we will start with the blue light. So an example is when I hold up all of these sheets of paper, you'll notice that it becomes very difficult to know which one was the blue sheet of paper. And the reason why is because if I shine blue light onto a red sheet of paper, then you're not going to see red because we didn't give it red. If I shine blue light onto a green sheet of paper, you're not going to see a green sheet of paper because we didn't give it green. So let me go back to the white light, and you can see that the blue sheet of paper is on top. And what I'm going to do is hold the green sheet of paper with it. And when we switch to the blue light, you'll notice that if I kind of jumble them around a little bit, it becomes a little bit more difficult to know which one was the green and which one is the blue. They both kind of look blue in color. I can do something very similar with the green. For instance, if I hold up all the sheets of paper to the green light, it becomes difficult to know which one was the green sheet of paper. And if I turn on the red light, you can see that again it becomes difficult to know which one was actually the red sheet of paper. So the idea is that if I hold up a blue sheet of paper to a source that has blue in it, it'll reflect the blue. But if I hold up the blue sheet of paper to a source that does not have blue in it, the paper is not going to reflect blue to your eyes because it's not being given blue to reflect. So the ability to see color requires the object to have the features to it to reflect the color that it's given. If I want to see a certain color, I have to provide that color for it to reflect to your eyes. Now, this leads me to the concept of absorption. Absorption is sort of the opposite of reflection. Absorption means something is taken in and it doesn't get bounced back, whereas reflection means something bounces to another location. So let me go back to the white light. You'll notice that this black piece of coal is very, very dark in color, very black, because it is a very good absorber. This is not a good reflector, it's a good absorber. And what that means is I'm giving it all of the colors of the rainbow, or essentially all of the colors of the rainbow, but it looks black to your eyes because it's essentially keeping all of the colors and reflecting almost none of those colors to you. Whereas the white sheet of paper is a very, very good reflector, but a very bad absorber. So the reason why the white sheet of paper looks white is because it's very good at reflecting what it's given, but it's keeping almost nothing. So this is reflecting quite a bit, whereas this is absorbing quite a bit. So you can see that they kind of go together, and of course that's why they look different. So this leads me to the idea, if I turn on the blue light, and I'm going to hold up the yellow sheet of paper, The reason why the paper doesn't look yellow is because I'm not giving it yellow. And so when I shine the blue light on it, you're going to get this weird looking color to it, and you're not going to get the yellow because what I'm doing is I'm providing it with a color that it can't reflect. And so it looks a little bit strange. Now, let me put the white light back on again. And so what you'll notice is if I were to say there has to be red light in here for it to look red, and if I hold up the green sheet of paper, the question is, where did the red go? Clearly, red is being given to this sheet of paper, but we don't see red. And the reason why is the red is being given to the paper is keeping the red. The green is being given to the paper, but the paper is reflecting the green. So this is very good at absorbing all colors that are not green. This sheet of paper is good at absorbing all colors that are not red, and this sheet of paper is very good at absorbing all colors that are not blue. So it can only reflect what it's given, and it keeps everything else. This piece of coal is very good at keeping everything, reflecting very little, and this sheet of paper is very good at reflecting almost everything and keeping very little. So they're sort of opposites to each other. So reflection and absorption have to go essentially together. If something is a very good reflector, it is typically a very bad absorber. And if it's a very good absorber, it's typically a very bad reflector. And you might notice this in the everyday world around you. For instance, if you have an automobile or a car that is painted black, even though it might be a very, very cold winter day, you get inside the car and you realize that it's very warm inside of the car. And that's because the black paint is very good at absorbing the sunlight, and even on a cold day, absorbing all that sunlight makes the interior very hot. But then when you have a white car, it reflects most of the sunlight, so the interior is much cooler for a white car as opposed to a black car. So emission and absorption and reflection are related. Emission, the third one, is the ability for an object to produce its own light and give that light to you. So something that emits is not reflecting light, it's not absorbing light, it is making the light itself. So this light bulb is emitting light, this sheet of paper is reflecting light, this piece of coal is absorbing most of the light. So emission, absorption, and reflection. So as you can see, reflection, absorption, and emission are important terms to understand. And the key thing to take away from that video that you just saw is the idea that reflection and absorption are sort of opposites to each other. So let's go back to our black body rules and let's talk about how they relate to each other. If you remember, before the video, we saw that for an object to have black body behavior, it must reflect no light that shines upon it. And you'll also notice that number 2 is that a black body is an object that absorbs all light that fall on it. And if you think about it, these two have to go together. If an object reflects nothing, it must absorb everything. As we saw in that previous video, objects are sometimes good at reflecting things, and objects are sometimes good at absorbing things. For a black body behavior, it must be both. An object reflects nothing and therefore must absorb everything. The third part of this is that if the object is going to have light come from it, that object is emitting light only as a function of its temperature. So the light that comes from the object is not because of reflection. The light that comes from the object is simply because of the temperature by itself. And in reality, rule number 3 is the concept of Stefan's law that we saw in the previous segment. So all 3 of these rules must be in place simultaneously for an object to behave with black body behavior and therefore produce light that we call black body radiation. To show you the idea of number 3 very quickly, let me go back to what we saw in the previous segment where I showed you some pictures that were related to how an object at various temperatures can produce light. So let me show you these pictures again. Remember that for rule number 3 is that an object will emit light because of its temperature only. You can see in this case the 3 pictures that we saw in a previous segment where the piece of metal is producing light at various colors simply because the temperature of the metal is changing. So this first one is reflected light. But down here, this is emitted light from the piece of metal, and the light that it emits is simply because of the temperature of the piece of metal. E is proportional to T. The bigger value of T, the bigger value of E. As the object is hotter, it will produce energy at different wavelengths, which means energy of different colored photons. In the next segment, we'll explore how we can relate this to the temperature of an object based on how we see it. I hope you'll join me.